Hello, great friends. I hope you are doing great. IBM is here with an episode of Learning Physics. Today, due to public demand, I've decided to record A-level physics paper 4.2, that is February-March series. As a result of too much demand from one of my students, I decided to record this today, even though I wanted to record it later on. So today I'm recording paper 4.2, solved past paper. I'm solving paper 4.2, February March. Don't forget, the link to the question paper is in the video description. You can download the paper. You can even pause the video, download the paper, try to attempt it, and then you can mark yourself following the video so that you try to assess how much you have learned in paper 4. Do not forget, no student fails physics if they raise 50% in paper 4. No student can fail physics if they raise 50% in paper 4. So if you spend much time practicing paper 4, I can guarantee that you are actually on the right track. You are actually succeeding. You are actually making it in your A-level exams. So without wasting time, I would like to take you to the document. So this is the paper that you are going to find in the video description. The link is attached to the video description. Just copy the link, paste it into your browser, or click on the link, and the document is going to be ready for opening in case you don't have it. Have the document in hard copy for easy practice. Okay, let's start. Cambridge International AS A-level, AS and A-level candidate name. My name is Ivan Brian. Ivan Brian, and my African name is this one here. This is where I derive the initials IBM. Okay, so the instructions, I think we are used to the instructions. This is paper 4, A-level structured equations. 9/7/02/42, February, March 2023. The paper is 2 hours. I don't know how long I will take to record this because I'll be explaining a lot of things. You must answer on the question paper. No additional materials are needed. Answer all questions. Use a black or dark blue pen. You may use an HB pencil for any diagrams or graphs. Avoid using pens for graphs because when you get a second thought, it becomes hard to change the graph. Write your name, center number, those ones are obvious. Write your answer to each question in the space provided. Avoid drawing arrows showing that the examiner that the answer has been written on another page. Now, fortunately, paper 4 has so many blank pages in case, especially for questions which require to prove or show that. You can try to first analyze them on the blank pages. Then you come up with a very precise and accurate method so that you can get those free marks. So this question paper has many blank pages, always. Do not use an erasable pen or correction fluid. Do not write on any barcodes. You may use a calculator. You should show all your working and use appropriate units. That is very important. The total mark for this paper is 100. So the total mark is 100. I will reduce the thickness. The number of marks for each question or part question is shown in the brackets. The paper has 32 pages. Any blank pages are indicated. So most of the constants are the same that we saw in paper 2. I think we have seen these constants, they are the same. The constants are the same and you must be used to this. I think apart from this is very new here. They have only been giving epsilon naught. Now they have added this so that students can use this instead of wasting time getting 8.85 times 10 power negative 12 times 4 pi, and then 1 over that. Some of the formula, we have seen this same formula in paper 2, so I will not go through them again. Gravitational potential energy, pressure of an ideal gas, simple harmonic motion, velocity of simple harmonic motion, electric potential energy. You need this, please. You need to know that these equations are available. Capacitors in series, capacitors in parallel, We have also seen resistors in cells. Some of these you may think they are not necessary in paper 4 because you see them in AS. But some of these concepts will be needed as we are going to see. Okay. So whole voltage, alternating current, all these ones we are used to them. Stefan Boltzmann's laws. Stefan Boltzmann's law, I think this is new. A Doppler redshift, that is also new because in the old series that was not there, but starting 2022, these were there. Okay, let us start now. Define gravitational potential at a point. Without wasting time, we know what gravitational potential is if you have been following my videos. If you have watched solved past paper questions, gravitational fields, you must be familiar with the gravitational potential at a point. So we said gravitational potential is the work done per unit mass in moving a mass from infinity to the point. So that work done to move a unit mass from infinity to a given point is what we call the gravitational potential at that point. The work done per unit mass in moving a mass from infinity to the point. Do not confuse gravitational potential with electric potential. If it was electrical, it would have been a unit positive charge from infinity to the point. Artemis is a spherical planet that may be assumed to be isolated in space. The variation with the distance x from the center of Artemis of the gravitational potential phi is shown in the figure. So here they have given us a graph of gravitational potential with distance. So this is potential times 10 power 7 with the distance. It is hard to follow these videos when you don't have the hard copy because my screen is very small. It cannot display the whole page. So I may be concentrating at small points. Okay. So this is the graph. This is gravitational potential times 10 power 7. And this is distance times 10 power 7 in meters. Okay, so as Artemis is a spherical planet that may be assumed to be isolated in space. The variation with the distance x from the center. So at 0, 0, that is at the center. Okay. The radius of Artemis is 4,800 kilometers. The radius is 4,800 kilometers. Determine the value of phi on the surface of Artemis. The radius is 4,800 kilometers. Determine the radius of Artemis. Determine the value of phi on the surface of Artemis. So we shall go back and hunt for the radius of 4,800 kilometers. So on the surface, I think here we shall have gravitational potential is on the surface, is going to be located at this point here. At this point here, this reading is going to be, this is where the surface is because it starts decreasing from this. It starts actually, because at infinity, it is maximum. So it starts at infinity, it is maximum, it is increasing. So it starts increasing from the surface as we move from the surface. Why am I saying it is increasing? Because it is negative. So it means as we move out from the surface, it starts increasing because it is negative. And at infinity, gravitational potential energy is 0 and it is maximum. So on the surface here, we have this value here, and the scale on the vertical is 0.5 divided by 10, which is 0.05. So this value here is going to be 3.55 times 10 power 7. So the value of phi on the surface of Artemis is going to be negative 3.55 times 10 power 7. Why negative? Gravitational potential is always negative. So this negative is not optional. For gravitational potential, the negative is a must. because potential is defined to be maximum at infinity, and at infinity it is zero. That means elsewhere it must be negative. And even when you look at the graph, you see that the graph is the value of gravitational potential is below the graph is below the x-axis. That means these are negative values. Therefore, we are saying the gravitational potential is going to be negative 3.55 times 10 power 7 joules per kilogram. Show that Artemis is 2.55 times 10 power 24 kilograms in mass. Show that the mass of Artemis is 2.55 times 10 power 24 kilograms. We have already seen that gravitational potential in the formulas which are given in the list of formula is equal to negative Gm divided by R. That is gravitational potential. But on the surface, we have seen that the gravitational potential is negative 3.55 times 10 power 7. But they told us the radius is 4,800. So I'll simply say that negative 3.55 times 10 power 7 is equal to negative G is the gravitational constant, which is given in the list of constants as 6.67 times 10 power negative 11, then times capital M divided by the radius, which is 4,800 kilometers. So that will be 4,800 times 10 power 3. So I'll make M the subject and I just press my calculator. The negative has cancelled, so I have 3.55 exponent 7 times 4,800 exponent 3 divided by 6.67 exponent negative 11. So this means our answer is going to be, when I make M the subject, so I'm finding M as 2.55 times 10 power 24 as required. So that is the value of M when I make M the subject there. Calculate the gravitational field strength G on the surface of Artemis. Gravitational field strength is defined as the force per unit mass. So it is going to be, remember the force is given by Newton's law of gravity. Newton's law of gravitation, that is the force is G, capital M, small m over R squared. Then gravitational field strength is force per unit test mass. So when I divide by mass, it means, by the way, this is just a by the way. So it means gravitational field strength is going to be capital G, capital M over R squared. So I'll substitute. Capital G is 6.67 times 10 power negative 11. Capital M is 2.55 times 10 power 24. Divide by R, which is 4,800 times 10 power 3, and this is going to be squared. So from my calculator, I have 6.67 exponent negative 11 times 2.55 exponent 24 divided by open brackets 4,800 exponent 3, but this is squared. So this is giving me 7.38. Now learn to write, I encourage you to write at least 3 significant figures, because I see, normally things are changing almost every year. So write at least 3 significant figures. So this is 7.38. So I'll write here G as 7.38 newtons per kilogram, because everything is in SI units. This is newtons per kilogram. Okay, a satellite is in an orbit at a fixed position above a point on the surface of Artemis. The satellite is located above the equator of Artemis at a height above the surface where the gravitational potential is negative 0.65. So the satellite is at a height where the gravitational potential is negative 0.65 times 10 power 7. It is located above the equator. That means the satellite is going to, if it was above the Earth's surface, it would be geostationary, but I can't call it geostationary, yet it is above another planet called Artemis. So it means we can say it is going to behave like a geostationary satellite, meaning to have the same period as the rotation of Artemis itself. So the period of the satellite is going to be the same as the period of rotation of Artemis itself. So we want to calculate the period in hours of rotation of Artemis. Let's first go to negative. Let's first go and look for the distance at which the gravitational potential is 0.65 times 10 power 7 joules per kilogram. So phi is equal to negative 0.65 times 10 power 7 joules per kilogram at a distance r equals to, let's check, negative 0.65. So let's see the radius from the graph, negative 0.65. Remember the scale on the x-axis is 0.05. So this is 5, 5. This is 6. This is 6, 5. 6, 5 is here, I think. This is 0.65 negative. So 0.65 is along this line. Let me try to find. Okay. So I see it is in the center here. It is in the middle there. So I'll draw a vertical line around here. The scale on the x-axis is, I think, there are 20 small boxes, 1 divided by 20. Each small box is 1 divided by 20. That is 0.05. So this is 20. I mean that is 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, and then in the center. So it is in the center here, in the middle of a box, it is going to be 2.6 and half a box. Remember, one small square is 0.08. So we have 2.1, 2, 3, 4, 5, 6. So that is 2.6. Then in the center there, it is almost 2.6. Since one small square is 0.05, I can say 2.63. I mean 2.65. I can say 2.65. No, 2.63, because half a box, half a small square is going to be, can I take 2.3? Let me first erase this line very well so that I can see. Okay, it is slightly beyond the center. So since it is slightly beyond the center, I'm going to take this point here. So 2.1, 2.2, 2.3, 2.4, 2.5, 2.6. Then one small square is 0.05. So this will be 2.6. Then in the middle of a box, or slightly above the middle of a box, let me take 2.64 or 2.63. I'll take 2.63. Okay. So I expect that there could be a degree of tolerance, so I'll take 2.63 unless otherwise. So I'm going to take that as 2.63. So R is going to be 2.63 times 10 power 7 in meters. Okay. So now we know that the gravitational force provides the centripetal force. So I will say gravitational force. I don't want to always write Fg, but I'll write gravitational force. Because when I write Fg, my students also write Fg. Gravitational force provides the centripetal force. What does this imply? It means that G, capital M, small m, over R squared is going to be equal to small m V squared divided by R. And you remember that V is equal to omega R, which is 2 pi R over T. I will divide this into 2. I still have enough space. So small m has cancelled, 1r has cancelled. So I have that G capital M over small r is going to be v squared. I'm squaring 2 pi r over t. So it becomes 4 pi squared r squared over t squared. Okay. So then I cross multiply this, or I make t the subject. So t squared is going to be equal to G. No, it is going to be 4 pi squared r squared divided by, I'm making t squared the subject, so this becomes r cubed when I cross multiply, so divide by g times m. Okay, so before I substitute these values, I want to be very sure. T squared is going to be 4 pi squared times r. Let me first leave r, I'll check it again. Over g, which is 6.67 times 10 power negative 11, then times 2.55 times 10 power 24, because this was the mass that we obtained. Let's check the radius again, or the distance from the center, because they said at a height above the satellite is located above the equator of Artemis at a height above the surface where gravitational potential is negative 0.65. And on the x-axis, we say the scale is 0.05. So this is 0.6. 0.6, so one small box, 0.65. So I moved like this. Okay, so we are here in this box here. On the vertical axis, we have seen the scale is 1 divided by 20, which is 0.05. 1 divided by 20, which is 0.05. So this is, whenever two small boxes will contribute, will make 0.1. So this is 2.1, 2.2, 2.3, 2.4, 2.5, 2.6. Once this would have been 2.65, but because it would have been 2.65, but because we are in between here, it would have been 2.65, but we have not reached a full box. That's why I took 2.63, approximate 2.63. Half of 0.05 is going to be 0.025. So I rounded off 2.63. Okay, I hope that is fine. Okay, so I will go with that one. In case you check and notice that it is slightly different, you can let me know. So this is going to be times, this is 2.63 times 10 power 7, and this is raised to power 3. Okay, so this is going to be 4 pi squared times open brackets 2.63 exponent 7, but this is going to be raised to power 3, divided by 6.67 exponent negative 11. Again, I'm supposed to also divide by 2.55 exponent 24. So I am getting 4.222. Then that is 2 square. That is 4.22 and 369. So I'm getting this as 4.22. This is 4.22 times 10 power 9. That is going to be, of course, seconds squared. They want the answer in hours, but I will first find the square root. So root of the answer is going to be 64980. So I'll write t as approximately 6, or I can find the root of root of open bracket 4.22 exponent 9. So 6, I'll just write 6.496 times 10 power 1, 2, 3, 4. That is times 10 power 4. Now that is in seconds. If I want this in hours, of course we know that 1 hour is 3,600 seconds. Therefore, I will divide this by 3,600 seconds, which is giving me 18. So this is giving me 18 hours. That is giving me 18 hours, although I'm still doubting this. The problem could be here on this value here, but it's approximately 18 hours to two significant figures. In case you get a different value for 2.63, which I've got here, am I using the scale wrongly? 2.1, 2, 3, 4, 5, 6. This would be 2.7. 0.55, 0.65. Okay, so that is what I'm arriving at. 18, approximately 18.0 hours. If you get a better value, you can let me know. But personally, I'm getting 18.0. Approximately 18.0 hours. I'll just write 18, two significant figures. So that is 18 hours. Okay. State one similarity and one difference between gravitational potential due to a point mass and electric potential due to a point charge. Gravitational potential due to a point mass and electric potential due to a point charge. Of course, I will begin with the similarities. We know that gravitational potential due to a point mass is inversely proportional to the distance from a given point. Similarly, electric potential due to a point charge is also inversely proportional to the distance from a given point. So that's one similarity. So we can say, because I want to write many here, I will say I will utilize this space very well. I'll begin by saying both are inversely proportional. Inversely proportional to distance from a point. If you remember, gravitational potential is negative G m over r, and electric potential is going to be Q over 4 pi epsilon naught times r. So both are inversely proportional to the distance from a point. That's one. Alternatively, you could also say both are defined to be zero at infinity. Both are defined to be zero at infinity. Electric potential at infinity is zero. Gravitational potential at infinity is zero. So both are defined to be zero at infinity. I'm not writing on these lines very well because I want to write more answers. After all, this is not an exam. So both are defined to be zero at infinity. Or you could say the points of equal potentials lie on concentric spheres in both fields, or for both. So I can say for both points of equal potential, which we call points of equal potential, or points at which potentials are equal, will lie on concentric spheres, which we call equipotential surfaces. So for both points of equal potentials, lie on concentric spheres. Which your teacher must have called equipotential surfaces or concentric circles. for which potentials are equal. So in both cases, if we have a point charge, say here, points of equal potentials or points at equal potentials will lie on a concentric circle around the point charge. So those are some of the differences. You could state one of those. I mean the similarities. Then for differences, of course we know gravitational potential is always negative. There is no argument about that. Why is it negative? Because potential at infinity is defined as zero, and yet the force between two masses is always attractive. Therefore, since the force is always attractive, moving a mass from infinity towards another mass, energy is got out. So that means energy is going to be less than zero. So we can simply say gravitational potential is always negative. Gravitational potential is always negative. Yet electric potential can be negative or positive. Electric potential can be negative or positive. If the charge is positive, electric potential is positive. If the charge is negative, electric potential is negative. Electric potential can be positive or negative because we can have attractive or repulsive forces with the charges. But for masses, masses always attract each other. So the gravitational potential is always negative. Okay, I want to switch off my internet. Okay, so this is the first blank page. Number 2. I've spent a lot of time on number 1 because I'm just moving slowly. State what is meant by ideal gas. So for an ideal gas is a gas which obeys the equation PV is equal to nRT, or it obeys the equation PV over T is equal to a constant at all temperatures and pressures. At all temperatures and pressures, where T is the absolute temperature, T is the absolute or thermodynamic temperature, absolute temperature. T is the absolute temperature, so you have to define this very well. T is the absolute temperature. It is the gas which obeys the equation PV is equal to nRT, but T must be the absolute temperature. Of course, nR is the constant. nR is a constant. nR is a constant where n is the number of moles. N is the number of moles or amount of substance. N is number of moles, and then R is the molar gas constant. So I'm just writing a lot because I want to exhaust everything that the examiner may be looking for in this particular question. The examiner may want to see that you know that this gas obeys the equation PV is equal to nRT. But he might also want to know that you know that this temperature T is thermodynamic temperature or absolute temperature. And also the constant is nR, where n is the number of moles and R is the molar gas constant. A fixed amount of helium gas is sealed in a container. The helium gas has a pressure of 1.1 times 10 power 5 pascals and volume 540 at a temperature of 27. The volume of the container is rapidly decreased to 30. The pressure of the helium gas increases to 6.7 times 10 power 6, and its temperature increases to 472 degrees Celsius. 742 degrees Celsius. No thermal energy enters or leaves the helium gas during this process. So this is called adiabatic. It is an adiabatic process. In other words, Q is equal to 0. No thermal energy enters or leaves the system. Show that the helium gas behaves as an ideal gas. Remember, for an ideal gas, PV over T should be constant. So we can say for an ideal gas, PV over T should give us a constant. So let's start with the initial state. For the initial state, P is 1.1 times 10 power 5. I will not change the value of V because I'm not solving anything. I just want to find if the constant is the same. So just say times 540 divided by the temperature, but of course for the temperature I must change it to Kelvin because this is addition. So this is 273 plus 27. So this is going to be 1.1 exponent 5 times 540 divided by 273 plus 27, which gives us 198,000. So this is 198,000. That is the constant there. Then let's check for the final state. For the final state, the pressure is 6.7 times 10 power 6. The volume is 30. Divided by the temperature, which is 742 plus 273. So we have 6.7 exponent 6 times 30 divided by 742 plus 273. So to three significant figures, we are getting 198,000. So this is 198,000. So to three significant figures, the constant is the same. To three significant figures, the constant is the same. So since the constant is the same, then we can simply conclude that the gas is ideal. The gas is ideal. Since the constant is the same, then I can conclude that the gas is ideal. In other words, PV over T is equal to a constant. The first law of thermodynamics may be expressed as delta U is equal to Q plus W. Use the first law of thermodynamics to explain why the temperature of the helium gas increases. Remember, Q was equal to 0. The system was, the process was adiabatic. No heat was entering or leaving the system. Therefore, we are just going to concentrate on delta U and W. And you notice that the volume changed from 540 to 30. It is a decrease. So if the volume decreases, it means work is done on the gas. So we begin by that point. Since volume decreases, work is done on the gas. And remember, when work is done on the gas, the work done is positive, which means delta U is also going to be positive. And since the work is done on the gas and Q is 0, so delta U is positive, it means internal energy increases. So internal energy, delta U increases. So internal energy decreases. Internal energy increases because delta U is positive. That means internal energy increases. It is also going to be positive. So internal energy increases. I want you to remember, for an ideal gas, internal energy is the sum of the random distribution of the kinetic energy of all the molecules that make up the ideal gas. The potential energy component of internal energy is zero. So it means internal energy is directly proportional to the total kinetic energy of the molecules. Also remember, total kinetic energy of the molecules is directly proportional to the average kinetic energy of the molecules, which implies that the temperature actually is going to increase because temperature is the average kinetic energy of these molecules. Therefore, since internal energy increases, it means total kinetic energy of the molecules has increased, which means the average kinetic energy of molecules has increased, therefore the temperature has increased. So I'll simply say hence temperature increases. Hence temperature increases. As simple as that. Remember, change in internal energy is directly proportional to the kinetic energy of the molecules, which is directly proportional to the average kinetic energy of molecules, and the average kinetic energy of molecules is directly proportional to temperature, or it is actually the temperature for an ideal gas. The average translational kinetic energy of a single molecule of an ideal gas is given by that expression, where K is the Boltzmann's constant and T is the thermodynamic temperature. Calculate the change in total kinetic energy of the molecules of the helium gas. So if kinetic energy is given by that, remember from the ideal gas equation, PV is equal to nRT. But remember, number of moles is number of molecules over Avogadro's number, then times R times T. And remember, R divided by NA, R over NA is K, which is which is Boltzmann's constant. So this is going to be N K times T, where K is Boltzmann's constant and N is going to be the number of molecules. So making N the subject, you notice that N is going to be equal to PV divided by KT. So I can find N from P was, I'll use the first stage, where P was 1.1 times 10 power 5. And the first volume was 540. It was in centimeters cubed. So I have to change it to meters cubed. Centimeters cubed to meters cubed, I will multiply by 10 power negative 6. Now it is in meters cubed, divide by K. K is given as 1.38 times 10 power negative 23. That is Boltzmann's constant. You can check in the list of constants. Then temperature was 273 plus 27, which is 300. So this is going to be 1.1 exponent 5 times 440 exponent negative 6. Divide by 300 times 1.38 exponent negative 23. So I'll write like 4 significant figures. This is 1.435. 1.435 times 10 power 22. So that is the number of molecules. So the average kinetic energy of all the molecules, or the change in kinetic energy of all these molecules, is going to be the kinetic energy. The change in kinetic energy of one molecule should be 3 over 2 K times the change in temperature, that is for one molecule, then times the number of molecules for all the molecules to get the change in total kinetic energy of the molecules. So this would be 3 divided by 2 times K, which is 1.38 times 10 power negative 23, then times the change in temperature. Of course, a change in temperature on the degrees Celsius scale is the same as change in temperature on the Kelvin scale. So when I subtract temperature on the Celsius scale, I don't need to again add 273. So I'll just say 742 minus 27. Or you can have both of them already converted in Kelvin and then you subtract. It is the same. Then times the number of molecules, which we have got as 1.435 times 10 power 22. So I have 3 divided by 2 times 1.38 exponent negative 23 then times open brackets 742 minus 27, then times 1.435 exponent 22. So I'm getting 212. I'll just write here 212 joules. Alternatively, somebody would just say, okay, the change in kinetic energy is equal to 3 over 2k delta T. Instead of adding times number of molecules, somebody will just add their PV over KT. So this will be times PV over KT, and the K cancels. So this person will now just substitute into this expression. This is another alternative. So it will be 3 over 2 times difference in temperature, which is 742 minus 27. Then times the pressure, which is 1.1 times 10 power 5, times the volume, which is 540 times 10 power negative 6, divided by the temperature there, which is 300. Because I use the pressure, I use this volume here of this pressure of 1.1 times 10 power 5. So this will give you the same thing. This will give you automatically, this will give you the same thing, 212 joules. I'm very certain about that. The mass of nitrogen gas in another container is 24 grams at a temperature of 27 degrees Celsius. The gas is cooled to its boiling point of negative 1.196 degrees Celsius. So it means there is a change in temperature. First of all, there is a decrease in temperature. And after a change in temperature, at boiling point, the temperature remains constant. Assume all the gas condenses to a liquid. When there is a change in state, when there's a change in state, the temperature remains constant. So first of all, there's a change in temperature, and when there's a change in temperature, the amount of heat is given by mc times delta change in temperature. And when there is no change in temperature, or when there is a change of state, the amount of heat is given by m times the latent heat. Therefore, I'm saying when there is a change in temperature from 27 degrees Celsius to negative 196 degrees Celsius, the change in amount of heat is mc delta T. And when there is a change of state, assume all the gas condenses to a liquid. Then the amount of heat is the mass times the latent heat. Therefore, the total thermal energy which is being removed from the nitrogen gas is going to be mc delta T when there is a change in temperature. And after that change in temperature has occurred, now there is a change of state. This will be plus m times the latent heat of vaporization. Note that the change in temperature is going to be from 27 degrees Celsius minus negative 196. Note very carefully that I'm not adding 273 here, because a change in temperature on the Kelvin scale is the same as a change in temperature on the degrees Celsius scale. If I want in degrees Celsius, I mean in Kelvin, I must add 273 on 27, and I also had 273 on 196. Then I subtract. But then that is not necessary, because I know the difference is going to be the same. So I'm now substituting. This is going to be the mass, which is 24 grams. That is 24 times 10 power negative 3. Then C is the specific heat capacity, which is given as 1.04. The change in temperature is 223 plus the mass is again 24 times 10 power negative 3. The latent heat is 199. So I'll just check my calculator. 24 exponent negative 3 times 1.04 times 223, then plus 199 times 24 exponent negative 3. So I am getting 10.3. So this is going to be 10.3. Instead of writing 10, you rather write three significant figures, 10.3 kilojoules. Is it kilo? Yes, 10.3 kilojoules, because I maintained this in kilojoules. I maintained also this one in kilojoules per kilogram. So the answer here is in kilojoules automatically. I didn't change from kilojoules per kilogram per Kelvin to joules. So the answer is in kilojoules. I think I changed in grams to kilograms. So the answer is in kilojoules. Number 3. An object is suspended from a vertical spring as shown in the figure. The object is displaced vertically and then released so that it oscillates undergoing simple harmonic motion. The figure shows the variation with displacement x of the energy E of the oscillations. So we can see the maximum energy here, 1, 2, 3, 4. I think that is 6.4 because the scale seems to be 0.1. Yes, the scale is 0.1, so the maximum energy is 6.4 millijoules. 6.4 millijoules. The kinetic energy, the potential energy, and the total energy of the oscillations are represented by one of the lines P, Q, and R. State the energy that is represented by each of the lines. Let's go back here. Of course, automatically P is total energy. This one is total energy. Then Q must be potential energy because when displacement is 0, the potential energy is 0. When displacement is 0, potential energy is 0. And when displacement is 0, kinetic energy is maximum. So R is kinetic energy, Q is potential energy. Okay. So P is total energy. Then we have said Q is potential energy. And R is kinetic energy. If you have watched the videos of simple harmonic motion, we have done that several times. The object has mass 130 grams. Determine the period of the oscillations. So we have already known from simple harmonic motion videos that energy is equal to a half m omega squared x naught squared. That is maximum energy. And also note that omega is equal to 2 pi divided by t, and I want t. So I'll just substitute. The maximum energy is given as 6.4 times 10 power negative 3 from the graph, which is equal to a half. The mass has been given as 130 times 10 power negative 3, then times omega squared, which is, I'll just write 4 pi squared over t squared because it is squared, then times x naught. That is the maximum displacement from the graph. Maximum displacement x naught is going to be, what is this value in the center? The scale on the x-axis is 0.04. So I have 1, 2, 3, 4, 5, 6, 7 and a half. 7.5 times 0.04. 7.5 times 0.04. That is 0.3. So I'll add 0.3 to 1.2. which gives me 1.5 centimeters. So this value is 1.5 centimeters. So I'll say times 1.5 times 10 power negative 2, and this is also squared. So I'm just going to press my calculator and I make t squared the subject. I'm just going to make t squared the subject. Okay. So making t squared the subject, I'll have a half is 0.5 times 130 exponent negative 3 times 4 pi squared times 1.5 exponent negative 2, and this is also squared. I'm going to divide by 6.4 exponent negative 3, so divide by 6.4 exponent negative 3. So that is 0.09, but I have to find the square root. So this is 0.090. Then I will find the square root of the answer. That is 0.30. So t is 0.30. So my answer here is going to be 0.30. State the cause of damping. Of course, damping is due to loss of energy caused by dissipative forces, such as in this case, we can talk about air resistance. So, loss of energy due to dissipative forces. Of course, dissipative, these are opposing forces. So, due to dissipative forces, such as air resistance. So, loss of energy due to dissipative or opposing forces. Due to dissipative or opposing forces, such as air resistance, for this case, because it is a mass on a spring. A light card is attached. So now damping comes in when we talk about a light card. A light card is attached to the object. The object is displaced with the same initial amplitude and then released. During each complete oscillation, the total energy of the system decreases by 8% of the total energy at the start. So I'll just select the total energy at the start be E naught, but we know it was 64 millijoules, 6.4 millijoules from the graph. So energy after 6 oscillations is going to be, of course, energy after every oscillation decreases by 8.0%. So energy that remains, I'll just call it E, energy remaining. Energy remaining after one oscillation. After one oscillation is therefore going to be 100 minus 8, which is 92%. So it is going to be 0.92 times the original amount of energy. So it means energy after 6 oscillations, energy after 6 oscillations. So it means I'll always be getting 0.9. I'll get 0.9 of this, again times 0.9 of the new value, again times 0.9 of that, which is going to be equal to 0.92. How many times? 6 times the original amount of energy. That is the energy which remains after 6 oscillations. So the energy lost is therefore going to be equal to the energy which the original amount of energy was it 6.0, was it 0.6, 6.4 millijoules. So energy lost is going to be, originally we had 6.4 millijoules minus the energy after 6 oscillations, which is going to be 0.92 power 6, then times E naught, which is 6.4. This answer is going to be in millijoules. So let's check. So you have 6.4 minus 0.92 ways power. Do I know how to use this calculator? Okay, power 6 times, no, then times 6.4. This is giving us 2.5 millijoules. Remember, this was in millijoules. I didn't convert. So this is going to be 2.5 or 2.51. No, it will be 2.52 millijoules. So the energy here is going to be 2.52 millijoules. Note how I arrived at 0.96, 0.92 power 6. After one oscillation, that is the energy. Let me do this for a layman who doesn't do mathematics. After one oscillation, we remain with 0.92 times e power naught. Then after another oscillation, the energy which remains is 0.92 of this. So it will be times 0.92. After another oscillation, it will be again 0.92 of what is there, so it will be times 0.92, again times 0.92 of what is there, again times 0.92 of what is there. This is first oscillation, second, third, fourth, fifth, then times again 0.92 of what is there. So that is the same as having 0.92 power 6, then times 6.4. So this is just for somebody who doesn't do math. State with a reason the type of damping that the card introduces. Of course, this is going to be light damping. This is light damping. Why? Because the amplitude of oscillation gradually reduces as the system continues to oscillate. So light damping because the amplitude of oscillations gradually reduces as the system continues to oscillate. So in practice, when a card is attached on the mass and then displaced again, of course the amplitude is going to gradually decrease. So this is light damping because the amplitude of oscillations gradually reduces as the system continues to oscillate. So it will continue oscillating but with a decreasing amplitude until it becomes zero. So that's light damping. Again, another blank page. State Coulomb's law. Of course, Coulomb's law can be quoted as F is equal to Q1 Q2 over 4 pi epsilon naught R squared, but this is not the law. These Q1 and Q2 must be point charges, so it states that the force between 2 point charges is directly proportional to the product of the charges and inversely proportional to the square of their separation. So the force between 2 point charges, it should be point charges, is directly proportional to the product of the charges and inversely proportional to the square of their separation, not to the square of the distance. It is the square of their separation. When you say distance between charges, without saying the square of the separation between the charges, then it is not going to be valid, or you will lose 1 mark. If you don't refer to point charges, you also don't get the second mark. Okay. A charged sphere X is supported on an insulating stand. A second charged sphere Y is suspended by an insulating thread so that sphere Y is in equilibrium at the position shown in the figure. Okay, let's use some mechanics here. When I draw a horizontal line here, and I call this angle theta, there is a force in this spring, which is going to be the tension. The sphere Y has a mass downwards, which is going to give us the weight W. The sphere Y is going to be repelled to the right-hand side, so there is a force Fe, which is the electric force. The sphere X is also repelled to the left-hand side with the same force Fe, which is to the left-hand side, which is the electric force. Okay, but before we move any further, we can find theta. You notice that sine theta is opposite over hypotenuse. Sine theta is 0.08 over 1.2. Okay, the charge on the sphere X is that the charge on the sphere Y is 64 nanocoulombs. Assume that the spheres behave as point charges. The length of the thread is 1.2. The centers of the spheres X and Y are separated by a horizontal distance of 0.08. Okay, on the figure, draw and label all the forces acting on the sphere. I've already labeled this. There will be a tension. That is tension. You don't just put there T. Then there is weight acting vertically downwards. You draw an arrow pointing vertically downwards, and you call this one the weight. And you will also draw an arrow pointing to the left, to the right-hand side, and you call this electric force. This is going to be the electric force because it is being repelled. So this is electric force. So that is what we are supposed to do here. Then determine the mass of the sphere. Remember, we have already seen from the graph, go back to the diagram. We have already seen that sine theta is equal to the opposite, which is 0.08 over the hypotenuse, which is 1.2. What is theta therefore? So theta is going to be the sine inverse of 0.08 divided by 1.2. So that is 3.82 degrees. So theta is going to be equal to 3.82 degrees. Okay, so we are going to do some resolving here on this diagram. The tension here has two components. I will change the color for that. For resolving, I will change the color for you. You can use a pencil. The tension has a component in the vertical. I will draw a vertical line here with the ruler. I'll draw a vertical line here. The tension has a component in the vertical which balances with the weight if there is equilibrium. And this component, if this angle is theta, this angle is also theta. This component is going to be T cos theta. So T cos theta is equal to the weight downwards. Then the tension also has a component in the horizontal, which acts on this same sphere. It is going to act in this direction, and this component is going to be T sine theta. And T sine theta will balance with Fe if the sphere Y is in equilibrium. So we have two equations. T cos theta is equal to the weight, and T sine theta is equal to Fe. Okay. So we have agreed that we have two equations. Number one, T cos theta is equal to the weight, which is mg. Let me go back to my column. T sine theta is equal to the weight, which is mg, which means that T cos theta, which is 3.82, should be equal to mg, which is the mass, times g, which is 9.81. I'll call this one the first equation. Then also T sine of theta, which is sine of 3.82, is going to be equal to Fe, which is the electric force. Let me first find the electric force. I'll first find the electric force. The electric force, remember, is given by Coulomb's law. So it will be Q1, Q2. The equation is given the list of formula. Divide by 4 pi epsilon naught times r squared, where r is the separation. So this is going to be equal to 996 nanocoulombs. So that is 96 times 10 power negative 9. Then Q2 can be 64 times 10 power negative 9. Divide by 4 pi. And the epsilon is given in the list of constants as 8.85 times 10 power negative 12. Then times r, which is the radius, or the distance, the separation of the two spheres, which was given from the diagram as 0.08, and this was squared. I'll first press my calculator here for simplicity. 96 exponent negative 9, 64 exponent negative 9, divide by 4 pi times 8.85 exponent negative 12. Okay, let me first divide that. Then I can continue further and divide by 0.08 squared. So this is 8.63 times 10 power negative 3. 8.63 times 10 power negative 3 newtons. That is the force to the electric field. Therefore, T sine of 3.82 should be equal to 8.63 times 10 power negative 3. This is going to be my second equation, and I'm going to solve these two equations. So I'm dividing the two. I'm dividing equation number 2, equation 2 divided by equation 1. Equation 2 divided by equation 1, so I have T sine of 3.82 divided by T cos of 3.82 should be equal to 8.63 times 10 power negative 3 divided by m times 9.81. I don't have enough space, but I'll utilize this one. So T cancels out, and sine of that becomes tan. So if I make m the subject, m is going to be 8.63 times 10 power negative 3 divided by, remember sine over cos is tan. If you're poor at math, you just press the calculator there is no problem. So when I take tan down, this will be 9.81 tan of 3.82. For you can cross multiply with your calculator if you are not good at math. But those good at math, they know that sine 3.82 over cos 3.82 is tan 3.82. So when I take it the other side, it will be 9.81 times tan 3.82. So I'll say 8.63 exponent negative 3 divided by 9.81 times 9.81 tan of 3.82. 3.82, which is giving me 0.013 in kilograms, or 0.0132. So this is 0.0132. So I'll write here 0.0132 in kilograms. So that is the mass. Calculate the total electric potential energy. Calculate the total electric potential energy between X and Y. So for electric potential energy, the formula is given in the list of formula. Potential energy is going to be one of the charges times another charge divided by 4 pi epsilon naught times R. So this will be 96 times 10 power negative 9, then times 64 times 10 power negative 9, divided by 4 pi times 8.85 times 10 power negative 12, then times R, which is, I think R is the separation between the two charges, which is 0.08. 96 exponent negative 9, 64 exponent negative 9, divided by 4 pi times 0.08 times 8.85 exponent negative 12. So this is giving me 6.9 times 10 power, or 6.91 times 10 power negative 4. 6.91 times 10 power negative 4 joules. An electron enters the region between the two parallel plates P and Q that are separated by a distance 18 millimeters as shown. The space between the plates is a vacuum. Potential difference is 250 volts. The electric field may be assumed to be uniform. If it is uniform, then we know that for uniform field, electric field strength is force per unit charge, per unit positive charge, which is going to be potential difference divided by the separation of the plates. So when a charge enters, it is an electron. When it enters, it experiences a force in the vertical direction upwards. And the force is constant and it is always upwards, vertically upwards. State the direction of the electric force on the electron. So I have just shown you here that the electric force is going to be vertically towards high potential. So I'll say towards plate P. Is it P? Yes, towards plate P. So it is towards plate plate P, or you can say upwards. It is upwards, or it is towards the top of the page. Then determine the magnitude of the force acting on the electron due to the electric field. So we have said electric field strength is the force acting on a unit positive charge, which is the same as potential difference divided by D. So I want the force, so the force is going to be charge times V over D. So we are talking about an electron, so that is 1.6 times 10 power negative 19. Potential difference was 250. The separation of the plates is 18. Was it 18? 18 millimeters. So it is 18 times 10 power negative 3. 1.6 exponent negative 19 times 250 divide by 18 exponent negative 3, which is 2.22222 up to power negative 15. So this will be 2.22 times 10 power negative 15. It's better you write more significant figures rather than writing very few and then you lose a mark. Explain why the electron does not follow a circular path. Of course, I have just mentioned that the force is always vertically upwards. The force is not perpendicular to the direction of the velocity. I mean, it is not perpendicular to the velocity of the electron. It is just vertically upwards. It is always in the same direction towards P, so it does not provide the centripetal force. Therefore, the electron does not follow a circular path. So I would say the electric force, is not always perpendicular. The electric force is not always perpendicular to the velocity, but it is always in the same direction towards P. It is always in the same direction. It's always in the same direction towards P. In that case, it is towards P. So it does not provide the centripetal force. So it does not For a force to provide centripetal force, or for a force in a field to provide centripetal force, the force must always be perpendicular to the direction of motion. Like a particle moving in a circular orbit, a particle moving around the Earth. Around the Earth, the gravitational field is always perpendicular to the direction of motion. If the particle is moving in a circle or the mass is moving in a circle, the gravitational field is always perpendicular to the direction of motion. In that case, the force is always perpendicular to the direction of motion. In that case, the force will always provide centripetal force. But here, the force remains in one direction towards the positive plate or towards plate P. Therefore, it is not always perpendicular to the velocity. And if the force is not perpendicular to the velocity, not always perpendicular to the velocity, it cannot provide centripetal force. So the electron does not follow a circular path. It instead follows a parabolic path. Okay, another blank page. A capacitor, a battery of EMF 12 volts, a resistor R, and a two-way switch are connected in the circuit as shown in the figure. Okay. Remember, when the capacitor is fully charged, the PD across it is the same as the PD across the battery. That one you should note that. The switch is initially in position S. When the capacitor is fully charged, that means when the PD across it is 12 volts, the switch is moved to position T so that the capacitor discharges. At time t after the switch is moved, the charge on the capacitor is Q. The variation with the t of ln of Q is shown in the figure. Okay. Show that the capacitance of the capacitor is 1.5 microcoulombs. Remember, when the capacitor is fully charged, the PD across it is the same as the PD of the voltage supply. Therefore, I will say that at t equals to 0 seconds, at t equals to 0, the PD V across the capacitor, before it starts discharging, V across the capacitor is going to be equal to 12 volts at t equals to 0. Then from the graph, from the graph, from the graph, from the graph, we notice that at t equals to 0, from the graph at t equals to 0, ln of q is going to be equal to, let's check, ln of q is this one, the scale here is 0.1, so this is 2.9. ln of q is going to be 2.9, ln of q is 2.9, and if ln of q is 2.9, then what is q? This implies that q is equal to, so I'll find if ln of q is 2.9, then what is q? So I'll press shift, ln of 2.9, which is 18.2. So if ln of q is 2.9, then it means q is going to be 18.2 microcoulombs. Okay, now I can find capacitance. By definition, capacitance is charge over potential difference. The charge is 18.2 a micro, that is times 10 power negative 6 divided by V, which is 12. So we have 18.2 exponent negative 6 divided by 12. So that is 1.5 microfarads. So I'll just say 1.5 a microfarads, or 1.5 times 10 power negative 6 farads, which is 1.5 microfarads as required. So there the capacitance is 1.5 microfarads. Note very carefully that is V across the capacitor when it is fully charged is the same as the battery supply, the voltage supply. And from the graph at t equals to 0, ln of q was 2.9, which gave me q as that. I just pressed my calculator, that shift ln. It's like finding the ant log, ln of 2.9, that is e power 2.9, which gave me 18.2. Then determine the resistance of R. Determine the resistance of R. Okay, so if you recall for a capacitor, there's a relationship between the time constant, the period, and any other quantity involved. Since here charge is what is being involved, so I'll say the charge at a given time is equal to the original charge Q naught e power negative 1 over RC, which is the time constant, then times t. If you consider ln, introducing ln, you notice that ln of Q is going to be equal to ln of Q naught. Because this is multiplication, it will be addition, so it will be plus ln of e power negative 1 over RC times t. So it means ln of Q is equal to ln of Q naught minus, because ln of e power will remain with only the power, so it will be minus 1 over RC then times t. So if you compare this with the equation y is equal to mx plus c, okay, I'll rearrange for those who don't do math. ln of q is equal to negative 1 over RC times t plus ln of q naught. All this mathematics is not necessary. Compare with y is equal to mx plus c. On the y-axis, we have ln of q. On the x-axis, we have t. It means the gradient is going to be equal to negative 1 over the pen has jammed. Okay, here's my pen. Okay, the pen is back. So the gradient is -1 over RC. Sorry for the pen, it had jammed. So if the gradient is -1 over R times C, so I'll just try to find the gradient on the y-axis from the graph. So let's go to the graph here. So we are starting from 2.9 and we are stopping at this point here. I think this is 1.1, 2, 3, 4, 5, 6. So this is 1.6. So y2 is 1.6, y1 is 2.9. Then x2 is going to be 5 point. This is 5.2 here. That is 5.2. So I'm finding the gradient. So the gradient is going to be 1.6 minus 2.9 on the y-axis. On the x-axis, I have 5.2 minus 0. So that is the gradient. Remember, we want to show that to determine the resistance of R, we want to determine the resistance of R. So this is going to be equal to 1.6 minus 2.9 divided by 5.2. That is negative 0.25. So I'm going to find RC. The negative has cancelled, or you can say -1 over RC is equal to negative 0.25. All this algebra is a wastage of time. So I'm making R the subject. So R is going to be equal to 1 divided by the gradient, which is 0.25, times C. Remember, I have just cross multiplied. The negative has cancelled out. And then I'm making R the subject. So C, we have obtained C above. It was 1.5 microamperes, microfarads. This is 1.5 times 10 power negative 6. So we shall have 1 divided by 0.25 times 1.5 exponent negative 6, which gives us 2.67 or 2.7 times 10 power 1, 2, 3, 4, 5, 6. So this would be 2.67 times 10 power 6 ohms. So I'll write 2.67 times 10 power 6 ohms. Then calculate the energy stored in the capacitor. So we know that energy can be equal to a half CV squared. So energy stored in the capacitor at equals to 0. So this will be initial PD. So this will be a half. Capacitance is 1.5 times 10 power negative 6. Then times 12 squared, which gives us 1.5, which is 0.5 times 1.5. A half, which is 0.5 times 1.5 exponent negative 6, then times 12 squared. That gives us 1.1 or 1.08 times 10 power negative 4. 1.08 times 10 power negative 4 or 1.1. Alternatively, I can use another method. Energy is going to be equal to a half Q. It is a half QV. Since we are looking at T equals to 0, so it is a half Q naught V naught. So this will be a half times Q. The initial charge is 18. We have seen it is 18.2. Then times V naught, which is, Q 18.2 times 10 power negative 6. Then times 12. So a half is 0.5 times 18.2 exponent negative 6. Then times 12, which is 1.09. So this is giving us 1.09 times 10 power negative 4. So to two significant figures, 1.1 times 10 power negative 4, that will be accepted, or any of these values will be accepted. The second identical resistor is now connected in parallel. Remember, for resistors in parallel, 1 over effective resistance is equal to 1 over R1 plus 1 over R2, but they are identical. If they are identical, it means 1 over total resistance is going to be 2 over R. That means total resistance is going to be R over 2. If they are identical, it means total resistance is half the initial resistance of one resistor. The switch is initially in position S when the capacitor is fully charged. The switch is moved to position T so that the capacitor discharges. At time T, after the switch is moved, the charge on the capacitor is Q. Sketch a line to show the variation of ln of Q with T between T equals to 0 and T equals to 5. So we have noted that the resistance is going to be half the original resistance, which original resistance is given by this value here. Okay, so I'll do this from this point. So our resistance, the new total resistance, effective resistance, is going to be a half of the original resistance, and the original resistance was given as 1 over the gradient, which was 0.25 negative, times the capacitance, which is 1.5 times 10 power negative 6. I want to have a more exact value, so this is going to be 1 over 2 times 0.25. I think that is 0.5 times 1.5 times 10 power negative 6. That is going to be our new resistance. So I'm going to go back to the expression, which is, where is that expression that I wrote? I'm going to go back to this expression here. I'll use this expression, ln of Q is equal to ln of Q naught minus 1 over RC, because R has changed. So using ln of Q is equal to ln of Q naught minus 1 over RC times T. I'm going to use the maximum time from 0 to 5. So ln of Q is what I want to find. Note this part is working for me to come up with a graph. Ln of Q is going to be ln of Q naught. We are starting from T equals to 0, which is 2.9. So this is 2.9 minus 1 over RC. It is 1 divided by R times C. And R is 1 over 0.5 times 1.5 times 10 power negative 6. So this is 1 over R, which R is 1 divided by 0.5 times 1.5 times 10 power negative 6, or you can press the calculator there. Then times C, capacitance, which is, the capacitance was 1.5 times 10 power negative 6. Then T, the maximum value of T I want is 5, because we are drawing the graph from 0 to 5. So times T. So I wanted this one to cancel out, so that I get 1 over 0.5, which is which goes up, and this space is not enough. Let me even change the color. So this working can be done on the blanker page because it's not part of the question. So ln of Q is going to be 2.9 minus 1.5 has cancelled out, times the 10 power that. 0.5, because it's 1 over 0.5, 0.5 goes up, times 5, which becomes 2.5. And this gives us ln of Q as 0.4. So when T is 5, ln of Q should be 0.4. At T equals to 5, ln of Q should be 0.4. So this is 1, 2, 3, 4. So the graph should come up to that point. So you are going to draw your graph between 0 and 2.9, and it will go to, on the x-axis, it will go to 5 and 0.4. I don't know what the tolerance will be after standardization by the examiners, but that is what I'm arriving at. So this is going to be the new graph. I'll draw the new graph here. It's not easy to draw this graph on a computer, but I'm going to try. Okay, so you can draw a better graph than mine. Me, I have tried. My graph is passing through this point, It is going to 0 and 2.9. The most important points are these ones that I've indicated there. So that is going to be the new graph. That will be the new graph. Note how I have arrived at it is the most important thing. I looked for ln of Q by using that equation. I substituted 1 over RC, but remember, resistance now becomes half. Why? For resistors in parallel, if they are identical, total resistance is half the resistance of one. That's why I divided it. I said a half times 1 over R, 1 over 0.25 times 1.5 times 10 power negative 6. Where did I get that? I got it from here. We had already computed resistance as this. So I took this instead of this. But you can also take that. Okay, so that marks the end of that question. Question number 6. A hollow probe. A hollow probe is placed in a magnetic field. The Hall voltage is 0. The Hall probe is rotated to a new position in the magnetic field. The Hall voltage is now maximum. Now note that if the plane of the Hall probe is parallel to the magnetic field, the Hall probe will give a 0 reading because Fleming's hand rules, left hand or right hand rule will now not be working there. It means the second finger is supposed to be pointing the same direction as the first finger, which is not going to be acceptable. The Hall voltage is now going to be maximum when when the Hall probe is at 90 degrees to the magnetic field. So explain these observations. These observations are easy to explain. Number 1, the reading is 0. The reading is 0 when the plane of the probe is parallel to the magnetic field. When the plane of the probe is parallel to the magnetic field, it means the current will be moving in the same direction as the field, so the reading is going to be 0. The right hand or the left hand rules cannot work here. And the reading is maximum the reading is maximum when the probe, or when the plane of the probe, I want to be specific, when the plane of the probe, not when the probe, when the plane of the hollow probe is perpendicular. Is perpendicular to the magnetic field lines. Okay, so here the plane of the probe is part of the magnetic field lines. Let me add lines there. And here the reading is maximum when the plane of the probe is perpendicular to the magnetic field lines. That means now the second finger is at 90 degrees to the first finger. Of course, even the thumb will be at 90 degrees. That means the Fleming's left hand rule or right hand rule can apply. The formula for calculating the Hall voltage VH is given by that. VH is directly proportional to B and I. Set the meaning of N. Of course, we have seen N several times. N refers to the number density of charge carriers. Or it can stand for number of free electrons, number of free electrons per unit volume. Explain why a hollow probe is made from silicon. We know that silicon is a semiconductor, and semiconductors have a small value of n. And remember, V from VH is inversely proportional to n. A small value of n will give a large value of VH, which is easier to measure. So we can say silicon is a semiconductor. Silicon is a semiconductor with a small value of n, with a smaller value. With a smaller value of n, you have seen that VH is inversely proportional to n. So it has a smaller value of n, so it gives a greater value, so it gives a greater and immeasurable value of, it gives a greater and measurable value of VH, because VH is inversely proportional to n. Okay. A hollow probe gives a maximum reading of 24 millivolts when placed in a uniform magnetic field of flux density 32 milliteslas. So we can see that 32 milliteslas is directly proportional to 24 millivolts, because remember VH is directly proportional to B. VH is directly proportional to B if all others are constant. The same hollow probe is then placed in a magnetic field of fixed direction and varying flux density. The hollow probe is in a fixed position so that the angle between the hollow probe and the magnetic field is the same as when the hollow voltage was 24 millivolts. The variation of the reading VH on the hollow probe with the time t from t equals to 8.6 is shown. Let's first find this, the value of V, the value of B corresponding to this value here. The scale here is 10 divided by 5, which I think is 2, 32, 34, 36. So X is going to correspond to 36 millivolts. What is X? So X is going to be equal to 36 millivolts times 32 milliteslas divided by 24 millivolts. So millivolts has cancelled. I want the value of magnetic flux density corresponding to the maximum value of VH here, which we have as 36. So we have 36 times 32 divided by 24, which is 48. So it means 36 millivolts correspond to 48 milliteslas. Okay. So let's now move to the question. A coil with 780 turns, so that is capital N, and a diameter of 3.6 centimeters, meaning the radius is 1.8 centimeters, is placed in this varying magnetic field. The plane of the coil is perpendicular to the field lines. That means B is maximum. Calculate the magnitude of the maximum electromotive force induced in the coil in the time between t equals to 0 and t equals to 8.6. So we know that EMF induced is equal to the change in magnetic flux density, magnetic flux linkage, which we know as BAN or NBA, divided by time. Now let's inspect and see where is the EMF maximum. EMF, this is the gradient, so EMF is directly proportional to the gradient. The rate of change of magnetic flux linkage, which is directly proportional to the gradient. Note that here, between t equals to this value of time, 3.2, up to t equals to 7.2, here the EMF is going to be 0. Reason? The whole voltage is showing that the magnetic flux density is not changing. There is no change in magnetic flux linkage. That's why VH is constant. The gradient here is smaller than the gradient here. So this is the part where we are going to get the maximum EMF. The maximum EMF will be got from the gradient this side. And this is 7.2, I think. and this was 8.6. So the time interval here is 8.6 minus 7.2, which is 1.4 seconds. And the magnetic flux density changes from 36 to 0. Therefore, that will give us the maximum EMF. So we shall simply say this is going to be equal to the flux density. The flux density, magnetic flux density we have seen is 48 milliteslas, so 48 times 10 power. This is very important here. What I did here before is very important to arrive at the magnetic flux density corresponding to 36 millivolts, because the whole voltage changes from 36 millivolts to 0. That's when we have an EMF induced. So this is going to be 48 times 10 power negative 3, then times the cross-sectional area, which will be pi r squared, and r area is going to be pi r squared, and r is 1.8 times 10 power negative 2, but this is squared, then times the number of turns, which is 780. The time interval is 1.4, for which the EMF is maximum. So 48 exponent negative 3 times pi times 1.8 exponent negative 2, but this is squared, then times 780 divided by 1.4. This is giving me 0.027 volts. So the maximum EMF is going to be 0.027 volts. So my answer here is 0.027. The hardest part is to get the 48 times 10 power negative 3. The rest people are familiar with them. You must have watched a topic called magnetic fields and electromagnetic induction, and that's when you must have gained confidence to answer such questions. Okay. Okay, that is the end of that. Let's go to quantum physics. A beam of light, white light, passes through a cloud of cool gas. The spectrum of the transmitted light is viewed and contains a number of dark lines. Explain why these dark lines occur. I want you to note that each dark line corresponds to a photon energy, and each photon energy corresponds to a single wavelength or frequency. So I'll begin with that. Each dark line corresponds to a single wavelength stroke frequency. Each dark line corresponds to a single wavelength stroke frequency, and each of those, or let me just say single wavelength, frequency, or photon energy. Because the wave energy of a photon, remember energy of a photon is hf, which is hc over lambda. H is always constant and c is constant. So each dark line corresponds to a frequency, which corresponds to a wavelength, which corresponds to a photon energy. However, a photon, many people write proton instead of photon. So a photon with energy equal to difference, a photon whose energy is equal to difference, difference in energy, a photon with energy equal to difference in energy of two energy levels is always absorbed or is absorbed. Only such photons whose energy is equal to difference in energy of two energy levels is absorbed by an electron, And what is the effect? And the electron is excited, and the electron is excited. Like some of you are excited to finish high school, so you're behaving like electrons. So a photon with the energy equal to difference in energy of two energy levels is always absorbed. This is absorbed by an electron, and the electron is going to be excited. On electron de-excitation, so these are 3 points. On electron de-excitation, when the electron de-excites, on electron de-excitation, on electron de-excitation, the photon is re-emitted. The photon is emitted or is given out, is emitted randomly in any direction. So I explained this in quantum physics. I remember when light passes through a gas, for example, some photons whose energy is equal to the difference between two energy levels are absorbed. On re-emission, they may not be emitted in the same incident direction. They are emitted randomly. They may be emitted in any direction. Such photons will not be present in the original direction of the incident light. Therefore, such photons will be missing on the screen. The position corresponding to energy of such photons or frequencies or wavelengths will be represented by darker lines. So that's why those darker lines occur. I think that explanation is enough to give you 4 marks. On electron excitation, the photon is emitted randomly in any direction, or the photons are emitted randomly in all directions. So that means some photons may not be re-emitted in the original direction, so they will be missing on the screen. Some energy levels for the electron in an isolated hydrogen atom are illustrated in the figure. Okay, the table shows the wavelengths of photons that are emitted in the transitions to n equals to 2 from the other energy levels shown. Wavelength is given here. The energy associated with the energy level n equals to 2 is negative 3.4 electron volts. Okay, calculate the energy in joules of energy level n equals to 3. So we know that the difference in energy levels is given by Hc over lambda. So this is going to be equal to E. Calculate the energy in joules of energy level n equals to 3. So let this be E1, or let this be, I'll call this one E1, and I'll call this one E2. So I'll say E1 minus E2. So this is going to be equal to E1 minus E2, because remember all these energy levels are negative. So this will be equal to 6.63 times 10 power negative 34, that is for H, times 3 times 10 power 8, that is for C. The wavelength was given, I think. The wavelength the energy associated with the energy level n equals to 2. The figure shows the wavelength of photons that are emitted in the transitions to n equals to 2. Okay, so this is going to be divided by 658 times 10 power negative 9, which is going to be equal to, remember energies are negative, so this will be negative E1 minus negative. E2 was given as, this is given as 3.40. So let the other one be E1. Let this one be E1, and this is E2, because transition is from n equals 3 to n equals to 2. So this is going to be E1 minus negative 3.4 it was given in electron volts, so I will say times 1.6 times 10 power negative 19 to change it to joules. So this becomes a plus. I'll just press my calculator so that I get the answer direct. 6.63 exponent negative 34 times 3 exponent 8 divided by 658 exponent negative 9. Then I will take this on the other side because it is minus minus. It was a plus. Again, it becomes minus. So I will say minus 3.4 times 1.6 exponent negative 19. So I'm finding negative E1 as negative 2 point. Is it negative? Let me check again. 6.63 exponent negative 34. Then times 3 exponent 8. Then divide by 658 exponent negative 9. Then plus, because this is minus, so I'll say plus 3.4 times 1.6 exponent negative 19. No, it is supposed to be minus because this one is a plus. So this is supposed to be minus 6.63 exponent negative 34 times 3 exponent 8 divided by 658 exponent negative 9. Then it becomes minus 3.4 times 1.6 exponent negative 19. Okay, so it means the energy here, negative E1, is actually negative, or I will just simply say E1 is going to be negative. Why did I put here negative? So E1 is going to be negative because the energies are negative, negative 2.41. No, it is 2.42 times 10 power negative 19 joules. So I will say this answer is going to be negative 2.42 times 10 power negative 19. Just a food of thought. I'll just remind you, the energies here, energy levels are always negative because electric potential at infinity is defined to be zero. So the work is done in moving, in taking an electron from the nucleus to infinity. And if the nucleus comes from infinity, where energy is maximum but zero, closer to the earth to the nucleus, if the electron comes from infinity closer to the nucleus, then it must be losing energy. Therefore, this is going to be negative. So that is, I think that is going to be the answer. Okay. Plutonium is unstable and undergoes alpha decay. Complete the equation to show the decay of plutonium. So alpha is 42. Uranium is, when I balance the equation, this is going to be 92, I guess. And this is going to be 234. The power source in a space probe contains 0.874 kilograms of plutonium. Each nucleus of plutonium that decays emits 5.59 mega electron volts of energy. The half-life of plutonium is 87.7 years. Capture the initial number of nuclei of plutonium in the power source. So we know that number of moles is number of nuclei over Avogadro's number, which is the same as mass divided by the molar mass. So this is going to imply that the number of nuclei N naught is going to be the mass, which is 0.874 divided by the molar mass. This is the molar mass in grams, so I'll just change it to kilograms. 238 times 10 power negative 3. Then times Avogadro's number, which is 6.02 times 10 power 23. So I have 0.874 divided by 238 exponent negative 3, then times 6.02 exponent 23. So this is giving me 2.21 times 10 power 24. So 2.21 times 10 power 24. Determine the initial activity of the source. We also know that activity is equal to lambda times n. And of course, we know that lambda is equal to ln of 2 divided by half-life, divided by t a half. So lambda is going to be ln of 2 divided by t a half. They gave us the half-life as 87.7 years. So it will be 87.7 years. Every year can be considered to have 365 days. Every day is considered to have 24 hours. Every hour is considered to have 3,600 in seconds. So it means the activity is going to be equal to the n, which is 2.21 times 10 power 24 times the decay constant, which is ln of 2 divided by 87.7, 365, 24, 3,600. So I'll press my calculator. 2.21 exponent 24 times ln of 2 divided by, open brackets, 87.7 times 365 times 24 times 3,600. So I'm getting the activity as 5.54 times 10 power 14. So this is 5.54 times 10 power 14. And of course, activity is going to be given a unit code in becquerels, or you can give it a unit as per second, because we have changed the time into seconds. Alternatively, we could work it out in another unit, but I think the most appropriate would be becquerels or per second. Use your answer in B Roman 2 to determine the initial power output from the source due to the decay of plutonium. So we know, since we have the number of nuclei, activity is the number of decays per unit time, and for every decay, the amount of energy given is 5.59 times 10 powers, 5.5 mega electron volts. So every decay gives us that amount of energy, and we have the number of nuclei decaying per second as 5.5. So power is going to be the total energy per second, which is going to be the number of nuclei decaying per second, which is 5.54 times 10 power 14. Then this is per second, of course. Then times the energy of each decay, which is 5.5. So I will say this is times 5.59 times 10 power 6 to change it from mega. Then times 1.6 times 10 power negative 19 to change it from electron volts to joules. So this is going to give us energy per second, which is going to be watts, joules per second, which is watts. So this is 5.54 exponent 14, 5.59 exponent 6, 1.6 exponent negative 19. So I am getting 495.5. 495.5 watts. So that's 495.5 watts, or 490. I don't want to write 500, but I can still write 495 watts, because I think this will depend on how much you rounded off here, but approximately 495.5 watts. Okay, now some people round off again. They first round off to this, and again they round off to 496. That is poor mathematics. The digit here after 5 is 4. You can't round off to 496. You either round off to 495 or 495.5. The space probe will continue to function until the power output from the plutonium in the source decreases to 65.3% of its initial value. So calculate the time in years for which the space probe will function. That is very easy. Remember we said activity is equal to A naught e power negative lambda times t. So now this time we shall change this to power. So the power should decrease the power should decrease to 0.653 of the original power. So I will say 0.653 P naught is equal to P naught e power negative. The decay constant, they want the answer in years, so I will just mention decay constant as ln of 2. Decay constant is going to be ln of 2 over half-life, which is 87.7 in years. So I'll say ln of 2 divided by 87.7, then I multiply this by t. So I introduce natural log. P naught has cancelled. P naught has cancelled. So I have ln of 0.653. When I get ln of this, I remain with only the power. So this is equal to negative ln of 2 over 87.7. And this is multiplied by t. So I will get t. T is simply going to be ln of 0.653 times 87.7, then divide by negative ln of 2. So I'm getting this as 53.9. So T is 53.9 in years. So the answer is 53.9 in years, and I think that is precisely correct. 53.9 years. An alternative power source uses energy generated from radioactive decay of plutonium-210. This isotope has half-life of 0.378 years, compared with 87.7, of course, years. The mass of the isotope needed for the same initial power output is 3.37 grams. Compare this with the other one was 0. The other mass required was 0.87 kilogram. 84 times 1,000 times 1,000, that is, what is that? 0.874 times 1,000, 874 grams. So compare with 874 grams, which is required, 874 grams, which was required for the other one. Suggest one advantage and one disadvantage of using polonium as the source of energy. We have seen an advantage already. One advantage, less mass is used. Less mass is used in this case. So less energy is needed to get the probe into space. Less mass is used. If less mass is used, it means less energy is needed to get the probe. We shall need less energy to get the probe into space. After all, we are just going to use a smaller mass, so it means we shall need less energy to overcome the gravitational potential energy to get the probe into space. One major disadvantage, you see that the half-life is very small. It means this is not going to last longer. This cannot provide energy for a longer period of time. So the disadvantage, the half-life is too short. Half-life is too short. Half-life is too short, so it cannot supply energy, or it will not provide energy. It will not provide energy, or it will not provide power for long enough, or for a long period of time. It will not provide power for long enough because the half-life is too short. in a very short time it will be exhausted, so it will not provide power for long enough. Okay, ultrasound is used to produce diagnostic information about internal body structures. Explain how ultrasound waves are detected. This time we want only detection. Remember, at the center of the piezoelectric transducer is a piezoelectric crystal. So we know that at the center of the transducer is a piezoelectric crystal, which is normally quartz. Is a piezoelectric crystal, which is quartz. It is a piezoelectric crystal, which is normally quartz. And when the ultrasound waves fall on the crystal, it changes shape or it vibrates. So when sound waves, especially ultrasound, when sound waves fall on the crystal, on the quartz crystal, it changes shape or it vibrates. Changes shape, or we can say vibrates. Okay, of course, the vibrations are the ones which cause an alternating EMF. These vibrations cause an alternating EMF. So it is these vibrations which cause an alternating EMF, which can be detected by electrical circuits. It can be detected and amplified, of course. It can be amplified. It can be detected and amplified by electric or electronic circuits. As simple as that. Of course, the EMF which is generated from the vibrations is going to be detected and amplified by electronic circuits into an image, which can be processed into an image by those electronic circuits. An alternating voltage V varies with the time t according to that equation. I think that is sinusoidal. Root mean square voltage is 66 volts. The frequency is 4.3 megahertz. Determine the values of V naught. Of course, from what we already know, V naught is going to be equal to root of 2 times V root mean square. So that will be root of 2 times 66. Root 2 times 66 gives us, 66 root of 2. That gives us a 93.3. So this is 93.3 volts. Now do not forget and you put 66 under the root. Then omega, they have given us the frequency. We know that omega is 2 pi f. So this will be 2 pi times the frequency, which is 4.3 times 10 power 6, because it is mega. So 2 pi times 4.3 exponent 6. So that is giving us 2.7 times 10 power 7 radians per second. So that is 2.7, how many? 2.7 times 10 power 7. Then the table 9.1 contains information about air and soft tissue. Determine the units of specific acoustic impedance. We know that specific acoustic impedance Z is the product of the density and the speed of the ultrasound in that medium. The density has units as kilogram per meters, kilograms per meters cubed. Kilogram per meters cubed. Then the speed is meters per second. So this gives us kilogram meters squared. Yes, meter per meter squared. And then per second. So the unit is kilogram meters squared per second. Kilogram per meter squared per second. That is the unit. Calculate the density of soft tissue. So density is going to be acoustic impedance divided by C. I think our soft tissue is 1.7 times 10 power 6. So it is 1.7 times 10 power 6 over C, which is 1000. The speed in that medium is 1600. So it is 1600. 1.7 exponent 6 divided by 1600. This gives us 1062.5. Or I can write 1100. Then use data from the table to explain why ultrasound cannot be used to produce an image inside an air-filled cavity such as the lungs. I think we discussed that in a unit called medical physics. We can first find the intensity reflection coefficient to remind ourselves. Alpha is intensity reflection coefficient is the ratio of the reflected intensity to the incident intensity on the boundary, which is equal to Z2 minus Z1 over Z2 plus Z1, and this is squared. So alpha, which is the intensity reflection coefficient, is going to be 1.7 times 10 power 6 minus 4.3 times 10 power 2 divided by 1.7 times 10 power 6 plus 4.2 times, 0.3 times 10 power 2, and this should be squared. If you are very experienced or much experienced with this will give you 0.999, which is approximately 1.0. We have done this several times, but we can still check it. 1.7 exponent 6 minus 4.3 exponent 2 divided by 1.7 exponent 6 plus 4.3 exponent 2. Then square this. You see it is 0.999, which is approximately 1.0, which means intensity reflected is approximately equal to incident intensity at the boundary. So we can say that since alpha, or the reflection coefficient, I don't want to write alpha now. Since intensity reflection coefficient is approximately equal to 1, it means almost all the ultrasound, almost all ultrasound is reflected at the boundary. So almost all the ultrasound is reflected at the boundary, or this means almost no ultrasound is transmitted. Almost no ultrasound is transmitted. This ratio here shows that the intensity reflected is equal to the incident intensity on that boundary, which means almost nothing continues further into the body. It is just reflected on the skin. Okay. Lastly, I think this is astrophysics and cosmology. A student observes different stars from the Earth. Give two reasons why some stars appear brighter than others. I think you observe this every day, but this is simple because one, a brighter star could be very close to the Earth, or it could be closer to you. That's number one. A brighter star, a brighter star could be closer to the Earth. A brighter star could be closer to the Earth. Number two, a brighter star could be having a greater luminosity in the visible wavelengths or in the visible spectrum. A brighter star could be having a brighter star could be having a greater luminosity. A greater luminosity. When I talk about luminosity, I'm talking about emission. It could be emitting more power in the visible wavelengths, in the visible spectrum or in the visible wavelengths. That's why we can see it as being bright, because we can't see it as being bright when it is not emitting power or maximum power in the visible spectrum. Or you could say a brighter star is hotter. You could just say a brighter star could be hotter. A brighter star is hotter. Of course, if it is hotter, we could say it is emitting more power in the visible wavelength. So a brighter star could be hotter, that's why it is appearing bright. But the most important ones are the first two. A brighter star could be closer to the Earth. A brighter star could be having a greater luminosity in the visible wavelengths. That means in the colors that we can see by our naked eyes. State what is meant by a standard candle. We know that a standard candle is an astronomical object which has a known luminosity. So this one is an astronomical object. An astronomical object of known luminosity. Astronomical object of known luminosity. If you have watched my videos on astrophysics and cosmology, I must have given examples of standard candles. One of them is the Cepheid variable stars, and the other one is I think we talked about the Cepheid variable stars whose luminosity varies periodically, and then we talked about the type 1 supernovae which implode rapidly at the end of their lives. So a standard candle is an astronomical object whose luminosity is known, and if the luminosity is known, such a standard candle can be used to take several other measurements. A spectral line from a star within a galaxy is observed to have wavelength 660.9 nanometers. The same spectral line is measured in the laboratory to have wavelength 656.3 nanometers. So you see that there is a redshift. Show that the speed of the star relative to the Earth is 2.1 times 10 power 6 meters per second. So this equation is always given. Delta lambda difference in wavelength is equal to V over C. So the difference in wavelength is 660.9 minus 656.3 divided by the wavelength in the laboratory, which is 656.3. This should always be the wavelength in the laboratory, in the denominator. This is going to be V divided by the speed of light, which is 3 times 10 power 8. So I'll have 660.9 minus 656.3 divided by 656.3. Then I multiply this by 3 exponent 8. So I'm getting 2.1 times 10 power 1, 2, 3, 4, 5, 6. So V is going to be 2.1 times 10 power 6 meters per second when I cross multiply here. Calculate the distance to the star. Calculate the distance to the star. The Hubble constant is given as that. Using Hubble's law, by Hubble's law, the recessional velocity is equal to h naught times d. Recessional velocity is directly proportional to the distance from the Earth. So the distance is going to be the speed, which is 2.1 times 10 power 6 divided by Hubble's constant, which is 2.3 times 10 power negative 18. So 2.1 exponent 6 divided by 2.3 exponent negative 18. So this is 9.1 times 10 power 23, or 9.13 times 10 power 23 meters. State and explain what can be concluded about the universe based on this change in observed wavelength. So first of all, you notice that the wavelength has increased. Wavelength has increased. Wavelength has increased. So we say light is redshifted. So light is redshifted. Because the wavelength has increased, we say that light is redshifted. What does this mean? This means that the galaxy is moving away from the Earth. So this means that the galaxy is moving away from the Earth. This means that the galaxy is moving away from the Earth. And if it is moving away from the Earth, where is it going? Hence, we simply conclude that the universe is expanding, and hence the universe is expanding. And if it is expanding, then the Big Bang theory can be accepted at some level. So the wavelength has increased. We have seen in the laboratory it is 656.3, and outside it is 660.9. So the wavelength is has increased, so light is redshifted. This means that the galaxy is moving away from the Earth, and if it is moving away, we can conclude that the universe is expanding. I think that marks the end of paper 4. 29 is a blank page, 30 is a blank page, 31 is a blank page, and 32 is a blank page. I hope I've tried my level best. In case there are errors, you will forgive me. I'm bound to make some of those errors, but I think I tried my level best to be a little bit accurate. You can leave a comment about the video. You can raise your concern. Nevertheless, I'm always ready to improve. So I wish you the best. See you. I will continue with solving the topical questions, especially I'm now on the formation of solids. Multiple choice questions. Please, paper 2 was solved, paper 4 was solved, topical questions were solved. For those who are new to the videos, please refer to those old videos. Bye bye. See you.